Okay, so we're gonna get started. So, thanks everyone for coming. We have political health here. So, we're quite happy to have Gavin Morley here from the University of Warwick. So Gavin did his undergrad and his PhD at Oxford, and then actually moved to a postdoc here in the US at the National High Magnetic Field Lab in Florida, before going back to the UK for a Royal Fellowship and then eventually to work. So he's now running a group at work. Lots of different things about NV centers, these really nice quantum systems that work at room temperature in diamonds. He's the founding director of Warwick Quantum, and he's going to tell us today about these really exciting ideas to use some combination of NV centers and levitated optomechanics with macroscopic objects to perhaps test the quantum nature of gravity. So, thanks, Gavin. Take it away.
Thank you, Dave. And let me also thank Dave for just really interesting day yesterday and today, visiting your labs, and great to see other labs like Jack Harris's lab has been amazing too. So I'm going to be talking, like Dave said, about some experiments we're doing and some theoretical proposals that we have towards testing the quantum nature of gravity. This is really going back to, such an important open problem. We've got general relativity for gravity. We've got quantum mechanics that explains pretty much everything else. The two theories don't work together, and we want to, there are theoretical proposals like string theory for how to make them work together, but what we really need is experiments. And so I'm really excited about, trying to build experiments like that. This is something that I'm doing, my lab is doing it with Dave's lab, also Andy Geraci's lab in Northwestern, and Sougato Bose and Anupam Mazumdar are theorists in UCL and Groningen, and we've all got a new proposal to work together, a new project where we're going to go after this. Actually, testing the quantum nature of gravity is really super ambitious and is far beyond what we're hoping to do on this 5-year timescale of the grant, but we're just, we see it as probably a LIGO-sized effort, but there's big error bars on that, but we're sort of just hoping to make some good progress in 5 years and help to sort of see how to build that really sort of exciting experiment. So I'm going to thank all the wonderful people that have been involved to make sure that I don't run out of time at the end, and thank all the wonderful organizations that have been funding us. So yeah, it's been very much a team effort, of course. And now I've got a whiteboard. You've got these marvelous whiteboards in here. I could be drawing, but on the whiteboards, but I sort of did some in advance here, and I'm going to start off with this wave function that is totally routinely demonstrated in some labs around the world. This is a superposition of an atom going through the left slit and the right slit, quantum superposition of an atom being in two places at once, going through a quantum double slit experiment, and this is just absolutely routine in lots of labs now. And then we can look at the other extreme at this wave function that Schrödinger was thinking about in 1935. I have to confess, I haven't read the paper. It's in German, and it's not that accessible. But and the paper involves some death, but we don't need any death here. This is just a superposition of the cat being inside the house and being outside the house. And I'm not sort of just squeamish about death, but it's just doesn't matter here. What matters is a superposition of this is a spatial superposition of some mass in this place and this place. And so this is the superposition distance, we call it, is the distance between two places. And so we want, we're not trying to put a cat in, this is much too ambitious. No one's trying to do something as macroscopic as a cat, but what we want to explore is this space in between. What's the most macroscopic superposition that's possible in terms of technologically possible and in terms of what nature allows. And for it to be a macroscopic superposition, we want a large mass, we want a large superposition distance, we want a long time, and all these things are important. And how important they all are depends on exactly what you want to do with it. But there's lots of really exciting physics that you can access if you could build something like this. And people have, and I'll show you some examples. But so we're really trying to, push this, like I say. And already we can look at this wave function that, you know, is routine in labs around the world of an atom in a quantum superposition. And we can ask about the gravitational effect of it. What is the gravitational effect from a mass in a spatial superposition? And this question sort of gets to the heart of what I want to talk about, because, you know, like I said, we have, you know, the good theory, the great theory we have about gravity is general relativity, which says that mass curves space-time, and then, you know, that's all fine, except here we have, but it's all fine, except that general relativity cannot cope with quantum mechanics or things being in a superposition. And so where we have a massive object like an atom in a spatial superposition, then do we have a superposition of space-times? Do we have, you know, and there are theoretical proposals for what's going on, like I said, but we really need experiments to guide the way. On the flight out, I was doing this sketch, which I think sort of sums it all up a bit more, and I can sort of try and work on the artistic skills, but you get the idea, you know, this would be like a superposition, you know, can we have a superposition of these two space-times, or is that not what happens? I think, and there's a whole history to this, going back to Einstein was aware that combining quantum mechanics and gravity, you know, is super hard. Bronstein really pushed that as well. Feynman showed up at this conference in 1947 and walked in and was talking a bit, and people were writing down what he was saying, and it was all very important, amazing stuff that he was saying, and he was really sort of saying that, you know, come on, surely, and you know, and this has sort of become the general opinion among physicists that, well, surely gravity needs to be quantum because of these sort of same arguments that you can have a mass in a superposition, and so he was sort of saying, you know, you can have, you know, the way it'd be great to be able to test this with this sort of macroscopic spatial superposition, a bit like this. And he was saying, you know, you have to do matter wave interferometry. So this is sort of a schematic of the kind of thing that we're thinking about, where we start with some object at the top, and we create this spatial superposition here like this. And then obviously it's useless just to measure it, because you're going to measure that it's on one side or the other, and that's boring. So with quantum mechanics and stuff like that, you want to bring the two superposition components back together and interfere them and look for some fringes. And so he was talking about that sort of stuff and was aware about that sort of stuff. But, you know, and people were saying, oh, you know, so could we do the, people were saying to him, could we do the experiment, you know, and it would be, and he was aware, and other people realized it's outrageously difficult. You know, you'd be sort of looking for the gravitational effect of this with some test mass, presumably. Gravity is just outrageously weak, so you know that with two protons, then the gravitational interaction is like 40 orders of magnitude weaker than the electromagnetic interaction, which sounds like a really lost cause, and it's not as bad as it sounds, because, you know, we can have objects like this or whatever that where the mass builds up, you know, it keeps getting bigger. You don't have negative mass, and so the heavier your object is, the more your mass gets. But whereas the, you know, the charge, like people like Dave has done the best experiments on this, showing that objects can be charge neutral, and you know, the positive charges and the negative charges can fight and cancel each other out, and so that really helps. But still, in spite of all that, you know, try and do the numbers on measuring, you know, the gravitational effects of a mass in a superposition like this, it's just outrageously too small an effect to try and measure, just like this. And so that sort of was all a bit stuck. All this stuff was a bit stuck for a while, until more recently, there's this improved concept about how to experimentally access this. And so Sougato Bose in UCL is a theorist who, I still remember him sort of sitting me down and telling me about this amazing idea. The idea is to not just have one matter wave interferometer here with, you know, a macroscopic superposition, quite a big mass, but if you can do it once, okay, well, just do a second one. And then the magic trick is to look for the interaction between them, and specifically to see if gravity can entangle these two objects. And what you're taking advantage of here is the fact that you've got incredible, when you're doing a quantum mechanical, so quantum sensing has become famous. And the cool thing about quantum sensing is that sometimes, when you're looking at a phase, you're trying to measure a phase, such as in an interferometer like this, it can be outrageously sensitive. Just like everyone says, oh, it's hard to make this macroscopic superposition because there's so much decoherence. So with quantum sensing, then you're using that great sensitivity to decoherence is your signal. You're picking up small effects like that, and so and so that's something you're taking advantage of here. But you have to then get rid of all the decoherence that would have otherwise be killing, the standard model physics decoherence that would be killing your superposition on either one of these interferometers. The idea is, that there's a stronger gravitational interaction between these two than there is between this component and this component, for example. And so that could lead to some gravitational entanglement between these two objects. And it's totally already been understood from the quantum information field that you can only entangle two things if you've got some quantum mediator. And so typically that quantum mediator might be a photon, for example. And so a photon can be in a superposition of, being there and not being there or whatever. And so in the same way, whatever this is, so this whole test wouldn't really tell us anything much about what gravity is, except it would just be testing whether gravity can be in a superposition. Because as quantum people, we would look at one of these interferometers and say, okay, so then we've got a superposition of the gravitational effect of this plus the gravitational effect of this. But, but the whole question is, can gravitational effects be in such superposition? And if you sort of put in some numbers for what you need, then they come out a bit like this. So this would be a 2 micron, and you can do it with different numbers and different, but this is sort of the design that we're thinking of. An object that's like 2 microns across. This superposition distance would be about 250 microns. This closest approach here would be about 200 microns. I can't get too close, otherwise standard model physics starts giving you strong interactions that are going to entangle things, the electromagnetic force, Dave's electric dipole moments, Andy Geraci's Casimir effects, stuff like that. Obviously, these would be charge neutral, which is sort of the easy part. And the whole experiment would take seconds. And so, that might sort of sound, if you're not familiar with all this very much, these numbers might sound vaguely, I think they sound vaguely reasonable, right? But actually, they're outrageously ambitious and, incredibly hard. Making this enormous superposition, very macroscopic superposition, is way beyond the state of the art. And I'll sort of show you some of the state of the art to give you a feeling for that. But still, it's not stupid. And so we're working on it and we're trying to sort of push it and find the best way to access it. And like I said, the general opinion in physics is that, presumably gravity is quantum and it will get quantized nicely one day. But there's a whole lovely history of people working on alternative ideas where gravity is classical. So John Van Oppenheim is sort of the most recent contribution to this. I think he's really sort of pushing it forwards. And to make that work, you need there to be some extra noise. And so if gravity is classical, then gravity has to introduce some extra decoherence onto your quantum systems in order for stuff to work. And that's, I think that's sort of vaguely reasonable. It could be very beneficial. It could, because it could it would probably collapse your wave functions objectively. It would probably be worried about the quantum measurement problem. And this would probably give you just an objective solution to it, because this would say that, Schrödinger equation goes on, Schrödinger equation goes on, instead of somebody in second year undergrad physics saying, oh, okay, now we're going to stop the Schrödinger equation, now we're going to do the measurement, then gravity would just objectively just say, okay, look, we're going to collapse the wave function now. So that would be would be nice from a theoretical point of view, I think. But equally, yeah. But so people think probably gravity isn't classical, but that's what we'd like to test with all this line of work. So a bit about the amazing experiments that other people have done along these lines, not trying to do this experiment, but trying to make a big macroscopic superposition. So there's amazing stuff here from the Kasovich lab. This is single atoms with an enormous superposition distance of 0.5 meter. But, for this quantum gravity thing, then the small mass really hurts you. The gravitational effect between individual atoms is so small that it really sort of makes it difficult to access this, this question of whether gravity can entangle things. What else? So clamped oscillators are amazing. We've got Conrad joining here soon, and a whole load of amazing work where people have got objects that are clamped down, like drum mode or something else. It's oscillating, and it can be, so it's really big masses, and they're, people put them into superpositions. There's more, there's loads more papers than this, but they're totally getting them into superpositions, but that superposition distance is really limited by the clamping, because you're holding on to some, diving board or other, it's not going to go into like a huge superposition of being in two different places, because you're just holding it rigidly. And so that looks like that's really going to limit the viability of this approach for this particular problem. Also, the superposition time is limited, because by clamping, then you're sort of, there's this decoherence that can come in through the clamp. This is working. Did I just, yeah. So this experiment is from Marcus Arndt's lab, and for me, then this is, and for most people, I think this is the most macroscopic spatial superposition. All these experiments are sort of heroic, super impressive experiments. Here they have molecules made up of 2,000 atoms, which are going through a grating experiment, just like a double slit experiment, really. The slit period is like 266 nanometers, so that's the superposition distance. That's pretty big. The 2,000 atoms, is way bigger than a single atom, but again, it's not enough mass to actually try and test quantum gravity. Of course, you can look at trying to extend all this stuff up. All these experiments, you can look at try and extend them up to see if gravity can entangle with them. But the downside of this is that the mass is not big, and it looks difficult to me to the beam of molecules traveling through like this. It looks difficult to push the mass up too much. Okay, so instead of molecules, then we can have levitated nanoparticles, like Dave's group work on, and my group works on, and obviously we have so here we've got Jack's group doing sort of levitated helium stuff, which is bigger than these nanoparticles. But here, so this is sort of 200 nanometer particles. These are optically levitated, and so amazing stuff here from Marcus Ostermeyer's group and Lucas Novotny's group, where these nanoparticles are cooled to the ground state, the quantum mechanical ground state of their motion. These particles, they're in a harmonic trap, so they're doing like three-dimensional simple harmonic motion, and they reduce the amplitude of that motion so that it's in the ground, got down to the ground state energy of that motion, which is a very quantum feature and is super impressive. But to push this forwards for the gravitational entanglement, then we would need something like a sort of getting these particles into a superposition, which people haven't done yet. But lots of people are interested in trying to do that kind of thing. Okay, so this is where sort of our proposals come in. So we've been working on this for more than 10 years now, and our approach, like Dave was mentioning, is that this particle should be a diamond with a single nitrogen vacancy center inside. Reason is that that color center has an electron spin, which I'm showing here as these arrows. And so then we'd like to make a superposition using a Stern-Gerlach type experiment, except back when Stern and Gerlach were doing it, and they weren't doing a closed interferometer. They weren't even really sort of caring about whether it was a superposition. They sort of had their, silver atoms sort of going up or down. But so for us, we need to start off with this electron spin. We can optically polarize it. So some of this stuff is routine. It's always funny how some stuff is so hard and some stuff is just routine, and yeah, that's fine. So in my lab, routinely, we sort of, we don't do this, but we have diamonds that are, 100 nanometers or a micron across with a single NV center in. I'll tell you some more about these nitrogen-vacancy centers, as long as I haven't been going on for too long. But yeah, we can polarize that single electron spin. We can use magnetic resonance to make this superposition of spin up and spin down, or I've drawn it here as spin left and spin right. And then in a strong inhomogeneous magnetic field, then that would provide a superposition of forces on the diamonds. The diamond gets pulled into a superposition of being in two places at once. And then we would need to bring it back together for the interference at the end. Okay, so we've been sort of coming up with lots of proposals about putting numbers to this and trying to think how to do it. And then, of course, that would be how we would want to do the gravitational entangle. Okay, so a little bit about this NV center in diamond. It's pretty famous now. Lots of people have probably heard of it. So this is what it looks like. We have diamond as this carbon lattice. You have one carbon atom replaced by nitrogen, and then next to it is a missing carbon atom, which is a vacancy. And in my lab, we're using that for magnetometry, measuring small magnetic fields, also trying to build a quantum computer. And this thing that I'm focusing on today, I get the impression that this is sort of a group that's all into fundamental physics. So I'm talking about that rather than the sort of applied stuff. And this is what Dave and me are working on together. Here's a nice picture of one of our diamonds. So you see it's not transparent like the gems that you see on rings. It's got this nice color because it's full of these NV centers. We're firing in green laser light here, and the red fluorescence is coming off. That's our signal. We measure how much of this red light is coming off, and it tells us the spin of this defect, the electron spin. And this is sort of a schematic of the sort of data that we get. The PL intensity is the photoluminescence intensity. So the amount of red that we're getting depends on the microwave frequency that we're sending in. So when we send in resonant, and this also depends on the magnetic field. So this is how we can do magnetometry, because obviously this is scene splitting, if you know all about that, and that depends on the magnetic field. And so with 2.87 gigahertz microwaves, then we see this resonance. We're flipping the electron spin and we see less red light coming off. And for higher magnetic fields, then we get a resonance, but we get these two resonances splitting off with magnetic field. I'm not going to go into the sort of energy levels and the transitions. It's all very simple, but I'm going to try and save time and skip over it. But the punchline for the NV center, the reason that the NV center is so popular is it has these awesome properties. We send in green laser light and it polarizes the electron spin, which otherwise you would put on like a 10 Tesla magnetic field and cool down to 4 Kelvin just to get the spin polarization. But instead, we sit at room temperature and shine in some green light, which is wonderful. Also, like I said, the amount of this red fluorescence that's coming off depends on the spin. And so then that means we can read out the spin state. And so we can do all this optically. It's really ideal for this levitated nanoparticle situation where you can't be connecting wires or anything like that. You want this nanodiamond or microdiamond levitating in vacuum, and you want to be able to look at the spin without touching the diamond. Okay, so And then just about the magnetometry, just to explain this and the magnetometry side, we in zero magnetic field, then we see this resonance here. And then as we increase the magnetic field, then we get the seam splitting. And then so we see two resonances, one here and one from here up to here. And so this is the explaining that data on the right. But yeah, we can do magnetometry. Just as an aside, I think I've got one slide about our magnetometry work. If you measure this, then you know that you've got a magnetic field of 9 Gauss. And then we do much more fancy stuff to make this more sensitive. So here's just a flash of 5 papers that we've had recently about this, and it's really pushing towards applications. It's very much sort of down to earth stuff where we've built fiber coupled diamond magnetometers, used them to image damage in steel. I've got the sensitivity down to 30 picotesla per root hertz. This was the most sensitive fiber coupled diamond magnetometer when we published it, and arguably still, but let's not get into that. We have measured the vector magnetic field and the tensor gradiometry, which is giving you more useful information. Here's us driving the magnetometer around in the back of a van, just for looking at, looking towards doing something that's useful for navigation. And there's loads of potential interesting, useful applications, maybe for fusion power or for going onto space missions and for medical applications and lots of interesting applications. Anyway, this is an aside. The magnetometry stuff side finishes there, and we'll get back onto the fundamental physics. And so this is just a scanning confocal microscope that we've built in my lab to look at single NV sensors. But this is quite a sort of a routine bit of kit in lots of labs, and that's what we would use for this sort of initial measurements that we do, just looking at the diamonds when they're not levitated. But here we are doing some levitation. This is some optical trapping, some optical tweezers. This is a zoom of our vacuum chamber, and we've got a microscope objective focusing some infrared light down here. This is a zoom of the trapping objective, and the green dot is the diamond that's optically trapped. And it's green just because we're shining some green light off it. So we were working on this stuff, and then so Anis is here. Anis and Karishma are visiting from Warwick with me. Anis was measuring some data on this and found that with this optical trap, as we increase the power of the optical beam, then the internal temperature of the diamonds was going up and up. And we were trying to do this lofty quantum gravity stuff, but you could see the diamonds were getting up to 800K or so, and then they would disappear and they weren't there anymore. And that makes perfect sense, because if you look up in the literature, then diamonds burn at sort of 800 Kelvin in air and in nitrogen, and they graphitize. And so we were destroying the diamonds like this, which was disappointing at the time, but it pushed us in a couple of good directions towards better things. So one of those improvements was to get away from using nasty yellow colored diamonds. We were using commercial nanodiamonds, and they're made from diamonds that look like this, and they're yellow because they've just got loads of nitrogen in them, 150 parts per million. So instead, we bought diamonds that are 1,000 times purer and nice and transparent. And we got our friend Ollie Williams in Cardiff to mill them, turn them into nanodiamonds. And this is good because being more transparent, the trapping light doesn't get absorbed so much. And when you're in vacuum, it's really hard to dissipate all that heat. But by being more transparent, then you're not going to absorb so much heat. So that was part of our plan. And that worked here up to a point. So this was at 4 millibar pressure with the optical trapping, when the diamonds were staying at room temperature, which is good up to a point. For the longer term, then we're going to need the internal temperature to be more like 1 Kelvin or 5 Kelvin, and well, modeling, then we could see that this wasn't going to be possible with, you know, even ultra pure nanodiamonds. The optical tweezers were not going to be compatible with having them at cryogenic temperatures, and so we realized that we need to move to a magnetic trap or something that isn't focusing in so much energy right onto where the diamond is. And so I'm going to come back to this point later, but for now I'm just going to mention another big benefit of these more pure nanodiamonds, which we were characterizing without the levitation. And so this is just showing how we made some silicon maps. We put these map features onto the silicon so that we could look in both scanning electron microscopy and confocal microscopy to see the diamonds in both cases. And so here's the scanning electron microscopy of one of our diamonds that's 200 nanometers across. After all these years, I still love toggling backwards and forwards like this, because we can toggle in the optical fluorescence from the confocal microscopy, and I love how it just overlaps with sort of, you know, there's fluorescence from where the diamonds are, but both pictures are giving us important information. And then once we're able, and so this means that we can then say, okay, what are the, you know, this is one NB center. We can see that from some of our optical measurements with the confocal microscope, and we know that it's this 200 nanometer guy, and then we can measure its spin properties. And so we measured the spin coherence time, and this was the longest spin coherence for these nanodiamonds at the time, and then we'll beat it in our next paper on the next slide. But this is you know, room temperature, and the spin echo coherence time is still the longest, 177 microseconds. Dynamic decoupling, and I'll give you, I think I've got a couple of animations about these spin measurements, if you don't know about Hahn echo and dynamic decoupling. But yeah, so these are sort of beautiful nanodiamonds that are very useful for sensing other stuff too, like people put nanodiamonds inside living cells, and the living cells just keep on living, and the nanodiamonds can be used for sensing, which is pretty useful, I think, but going to be pretty useful for biologists and biochemists. This was a nice thing about our diamonds. Here's an animation that I made more than 10 years ago. I have to keep showing it because it took me some time coding this. So to measure the spin coherence time, we start off doing a spin echo. We make spin superposition with this 90-degree pulse, but then they fan out, which looks like decoherence. And this refocusing pulse, this 180-degree pulse, refocuses that decoherence, and we get back to an echo, which is a nice signal. So this is the Hahn echo, famous Hahn echo sequence. And then to measure the spin coherence time, and then make this time t longer. As you can see, so this is this time t, and as it gets longer, then the echo gets smaller. That's because there's actual real decoherence happening that we can't get rid of with this this refocusing pulse. So this is sort of how we do these measurements of the decoherence time. And then with dynamic decoupling, we send in more and more of these pi pulses, maybe sometimes 10,000 of them, just to really improve that spin coherence time. And so doing stuff like that, and also making even more fancy nanodiamonds, then we've sort of got even longer spin coherence times. Also our T1 times are the longest in nanodiamonds, and T2 star times are also the longest. This T2 star is the spin coherence without doing any pi pulses, with no Hahn echo. And this was helped by the fact that we've got carbon-12 isotopically pure nanodiamonds, and yeah, and also, you know, low levels of other impurities. We've looked at 5 different diamonds in this sample. Okay, so yeah, so that's the kind of stuff that we want to levitate. But if we look at this spin coherence time, then it's sort of on the order of milliseconds. And I was saying for quantum gravity, we need more like a second, and that seems like quite a big difference. Good news is that once you get to sort of spin coherence times like this, room temperature, it basically means that your NV sensors are about as good as they come. And when they're good like that, then you can cool them down and improve the spin coherence. So by cooling them down, then you make the T1 time longer. So the T1 is the time scale on which they can store classical information, and it's limited by phonons. People call, like this is this paper from Ron Walsworth's group, where they cooled the diamond sample down to only to 77 Kelvin, and the T1 time became much longer, and then that allowed the spin coherence time to get much longer, up to the order of a second. And this required this sort of 10 to the 4 pi pulses that I was mentioning. So there's lots of dynamic decoupling. But this is showing that, there are more recent papers extending these times further up beyond a second. And so these NV sensors, electron spins, can store the quantum information for this sort of time. But it's a general feature of all this quantum gravity experiments that we'd like to do, that we're always just asking for the absolute, hero values, the best values that anyone's ever done, and then a bit more in sort of several different, really, difficult areas of experimental work, and needing to do them all together. And there's I had this great mentor called Marshall Stoneham, and he sort of said, "Oh, just because you can ride a bike and juggle doesn't mean you can do both at once." And that was many years ago he said that, but I feel like that often comes up in my head. And then he said this in the meeting. I did say, "Okay, I reckon I could do that actually," and I did go off in video. I can show you the video somewhere. In these slides. But yeah, so those are the sort of challenges that we're up against. And so, we're going to need lots of dynamic decoupling to preserve this spin. And in this 2020 paper, Martin Plenier, Norman was pointing out that we could do motional dynamic decoupling as well. So not just spin dynamic decoupling. So dynamic decoupling gets rid of sort of noise, get rid of your sensitivity to decoherence in the environment. And what's going on won't sort of go into exactly what's happening here, but there's not enough time, do ask me afterwards. But the situation we're envisioning here is this diamond, and we drop it because we don't want it to be clamped at all, or even trapped. Even just, the sort of trapping that we do is enough to sort of stop the superposition distance from becoming as huge as we would like. But even if you drop it with this inhomogeneous magnetic field, then the inhomogeneous magnetic field causes that inhomogeneous magnetic field still that you need for the Stern-Gerlach effect. It still causes some trapping in one dimension, and so it causes these oscillations in green, and they look like they're a pain. But with this motional dynamic decoupling concept, then you can take advantage of them and use them for the forces of good. And so for that, we've got, instead of the green, we use the blue and the red. And so we have the diamond to start with, and we make the spin superposition, and then the superposition distance sort of goes left and then right, and then left and then right. It weaves backwards and forwards, but the amplitude's getting bigger, which is great. So that's what we want, is this big superposition distance. And then any sort of static noise that this motional quantum state would have picked up as it's falling down, you can decouple from it, and you can intuitively see that, because the red is spending part of its time over here, but the blue is also spending part of its time over here. And so then it's like both of them are sort of seeing the same problems, and that's cancelling it out. Okay, so I think this is part of the solution. Will be part of the solution. Unfortunately, though, if I just go back, so the way that this works is we send in microwave pi pulses here, pi, and flip the spin. And so that's great, because remember, on the other slide here, they're saying we want like 10 to the 4 of these pi pulses to have good spin coherence. So that's good that we're sending in some of these pi pulses, but the numbers don't work out well. The numbers work out meaning that we're only sending in these pi pulses too rarely. You know, this time gap is too big. We need to be sending in a lot more of these pi pulses to preserve the spin coherence. So to overcome that, Ben, PhD student, and me, and Sougato Bose were working out this concept for overcoming that. And our solution, well, this solution that we were proposing, I mean, this is like super difficult experiment that we're not building at the moment, but this solution we were proposing was to have magnetic teeth down here, all the way, the diamond dropping down here, and as it comes down past these magnetic teeth, this is COMSOL simulation of the magnetic field, this is this COMSOL simulation of the magnetic field, and so as the diamond drops down, it would see this inhomogeneous magnetic field we want, which would reverse, would go one way and then the other, and one way and the other. And as the diamond drops down and sees a different direction for the inhomogeneous magnetic field, then you send in a pi pulse on the spin so that you can send in lots of pi pulses, however many you want, and your superposition distance can keep on growing. So that's a proposal that we had. You know, I think it's super. There's lots of experimental challenges with actually doing this, but we're all just sort of coming up with lots of these concepts and proposals to try and get towards something that's more and more feasible.
Do you get any heating from the pi pulses?
So there would be some heating. Yeah, I wouldn't. Yeah, I think that we have lots of bigger problems to worry about. I think that the pi pulses wouldn't, you know, the microbes wouldn't particularly heat the diamond. The diamond's very insulating, and so I think, yeah, there's some dielectric loss in the diamond, but I think it's, you know, we have a list of sort of 10 or so big problems that we worry about. That doesn't make it off the list. Yeah, thanks. So, yeah, and so we were including some of this motion dynamic coupling in here as well, which is amazing for fixing problems like tilt noise, for example. So in such a tall thing, then tilt noise would be totally lethal without this sort of brilliant motional dynamic coupling, which I think would fix tilt. Okay, and now remember I said that we had these experimentally, we had these more pure nanodiamonds which didn't heat up in the optical trap, but long term we need to have cryogenic temperatures for the internal temperature of the diamond. And that wasn't going to be compatible with the optical trapping. So we thought we wanted a magnetic trap. And so we built one because, hey, that's our job. People pay us to do this stuff, amazingly. So we knew in the literature there was work from these two groups, Brian Durso's and Jason Twomley's, on magnetic trapping of nanodiamonds. And I just saw in Jack's lab there's a Durso style magnetic trap like this, which is very cool. We picked this Twomley style trap where you have these neodymium, strong neodymium magnets north-north facing each other. So there's zero magnetic field in the middle, and so diamagnetic things, you know, like to be in zero magnetic field. They get trapped here, the vacuum, and yeah, so we built one for ourselves. It's a vacuum chamber. We've got these two sharp magnets like this, and here's a video of oops, I said it's a video. I should have kept quiet in case it doesn't work. It does work. So we've got, you can see the this is one of the magnets, this is the other magnet, and this is twinkling diamond in the middle. And we did some feedback. Anis and Krishna have done some feedback cooling where we measured the position of this diamond in real time with lasers and with a laser, and we, you know, as the diamond's doing its simple harmonic motion, we sort of whack it to try and reduce, you know, to reduce its amplitude, and that that's working up to a point at the moment. And yeah, the amazing thing about magnetic traps is that they're not pumping energy, they're not pumping heat into the diamond. It's very sort of passive in that way, which is nice. And it gives us this big inhomogeneous magnetic field. You have like 10 to the 4 Tesla per meter magnetic field in homogeneity here, which should give us some Stengola force on the spin. Okay, and I'm pretty much coming to the end. So this is a nice, pretty picture I made of the grand experiment we'd like to do. Talked about how dropping levitated nanodiamonds past magnetic teeth could test the quantum nature of gravity, and experimentally how our more pure nanodiamonds and they're more transparent, so they don't heat up so much in an optical trap. Even if it's not an optical trap, we've got to send in lasers to control, to measure the position of the diamond and to polarize the spin and to read out the spin. So being transparent is always going to be super important. And the long spin coherence time is also super important, which is much better because we've got these more pure nanodiamonds. So in case you're the sort of person like me that likes to sort of take photos of all the papers, then you're welcome to. But yeah, otherwise, thanks for listening and happy to take any questions. Do you have any questions? Also, like I said, this MAST-QG is the name of our new project. We've just got a super rudimentary webpage, finally, just recently set up. These are the five of us working on it in collaboration. It's funded by Sloan and Moore Foundations, and yeah, looking forward to seeing how that goes.
What's the spacing on the magnetic teeth?
On the teeth, yeah, so we try and remember or have a look. So you can you're free to choose it, but so here we have this in microns, so it's about sort of 100 micron peak size. You're sort of free to choose it depending on how often you want to send in the pi pulses, and depends on how fast the diamond's falling. So in this design, we actually say that we need this sort of 1 meter initial thing so that it speeds up, so that they're going fast enough so that the diamond can pass a tooth in a good time, a nice short time, so that we can get these pi pulses in quickly, with a high enough rate.
Is there any advantage to having the gradient in the spacing because they're speeding up?
Exactly, yeah, we did think of that. So either, so as the diamond falls, then it speeds up, and then either you need to change the spacing, but we thought it would just be easier to send in the pi pulses more quickly as they fall, rather than trying to make it. It's quite demanding making this, but not, like everything in this proposal, not utterly stupid, just sort of all a bit demanding.
Do you have an estimate on the vacuum required to allow these things to interfere?
Yeah. I should probably just show the list of all of our terrible problems to save everyone trying to think of what all the terrible problems are. So we were just talking about the vacuum yesterday, and we think it's about 10 to the minus 18 millibar, which coincidentally is just sort of the absolute, probably just about the absolute best pressure that anyone's ever achieved. So like I said, everything about this is sort of super demanding. I could try and find our Excel spreadsheet, if you like, with all the different, it's an incomplete spreadsheet, but it's our attempt at listing all the problems. The opportunities, sorry.
Maybe while you're looking at that, one thing that I remember from these experiments is that you can make these objects neutral, but they're stuck with a lot of dipole moments.
Yes.
How big a problem is that when you're trying to sense the gravitational effect?
Exactly.
Yeah,
Go on, Dave.
I guess our job here is to measure the dipole moments of diamond, which people haven't done yet, but if they're the same as silica of that size, then you have to reduce it by a factor of a million times stronger than the gravitational force. So that's going to be a big job, and we think that'll be the dominant interaction between the diamonds at 100 micron distances.
But I'm an optimist, like this, students will tell you, and so my take on this is that Dave thinks that, in his silica, then there's a lot of impurities. What was it, like part per million or something?
And it's more like 10% impurities for the kind of maybe 1%,
I've just given Dave some nanodiamonds with like 1 part per billion levels of impurity, and so and they're not spherical. yeah, and we just don't know what the inbuilt electric dipoles in these diamonds are. But as an optimist, I'm gonna hope that, and that the incredibly better purity might sort of radically improve the electric dipole moments. But yeah, it's exciting just to have an experiment almost ready, or rather no, ready, that might just be able to sort of test that. So yeah, let's look at some of the problems. There's the Einstein-de Haas effect, Humpty Dumpty effect, you might not have heard of. So there's this sort of mid-80s, Schwinger and a couple of other smart people were thinking about pretty much this problem of, a macroscopic closed interferometer with a macroscopic superposition. And they were sort of pointing out that if you sort of do that matter wave interferometry, you really need good overlap when the the wave function. You can't just sort of bring them back, kind of nearby. You've got to actually get good wave function overlap to see interference. And so this is called the Humpty Dumpty effect. I guess when you're Schwinger, then you can come up with stupid names. But I say that I've come up with terrible names for things in the literature as well. But Humpty Dumpty, you couldn't put them back together again. So they were saying that it looks really hard from the maths to sort of get the to get that interference from getting your two wave function components to really overlap. But so yeah, there's a lot of theory work on that. You need that to work for the linear momentum and for the angular momentum. The electric charges, we're pretty sure we can just, like Dave and others demonstrated, you can just electrically neutralize things, so that should be okay. Dipole moments is very much important. Pressure, yeah, probably like world record levels of pressure. Temperature, we think you only need like this far right hand column is the sort of the quantum gravity thing. And we think that you only need sort of 1 Kelvin or something to do the quantum gravity test. There's problems with unwanted, oops, sorry, bit of a lag on it. There's unwanted electron spins in the diamond, unwanted nuclear spins. So again, would be necessary to improve on on the state of the art in sort of the pure the unwanted spins in your diamond. Otherwise, they're worse than the NV center that's supposed to be doing good things. Vibrations and the gravity gradient noise look quite extreme. This experiment might end up underground to avoid people driving their Harleys around too near the experiment. Yeah, the tilt noise sort of looks terrible, but I think that this motional dynamic decoupling would fix it. Yeah, so feel free to do please shout out other flaws. We're always glad to hear about other flaws, but yeah, this is enough to be getting on with.
I have a question. So just that a lot of magnetic fields. So how large do you expect the element to move horizontally?
Let's think. So on this sort of picture, then we were concerned about being limited, about hitting the teeth with a tilt. Because we've also got this this diamagnetic oscillation means that the diamond isn't just falling straight through here, it's sort of oscillating.
Okay.
I'm afraid I forget the numbers when we went. So this is about 200 micron gap in the middle over a sort of a 1-2 meter drop, and so we were pushing it. We were up close to sort of the diamond crashing into the teeth, which doesn't exactly answer your question, but gets close to sort of answering your question, I think.
Yeah. Thanks.
But yeah, you could imagine sort of working hard to make sure your whole experiment was very vertical, but you would worry about like thermal expansion and all sorts of any normal sort of problem you have with like with no background experiments, it's liable to sort of come in.
So I have a question about your magnetic trap. You were talking about superposition of hundreds of micron, and yesterday you were complaining about diamonds moving at the scale of tens of microns. So how are you supposed to create such a large superposition if you can't safely trap the diamond over like hundreds of microns? Or is that something that we eventually need to do the experiment?
Sure, yeah, good question. So we would, I mean, with good feedback cooling, we should be able to have the diamond, you know, in a particular place, hold it to, you know, better than a nanometer, right? And then to get that big superposition distance, we're going to need to do something. Well, at the moment, it looks like best we can see is that we need to do something sort of ambitious like this, like a big drop, and the big superposition distance would only come sort of in the middle of this big drop. And we have to get it back together again for the closing the interferometry. But yeah, there was also ideas that avoid a drop, like so in Brian Durso's magnetic trap, then there's this long axis. So it's interesting to think about types of trap like this, where it's well confined in two directions, but it's not well confined at all in the other direction. And then if you could try and make the big superposition be in that direction, then you could have a long time to do that big superposition without needing to drop something. I really like the word dropping thing.
Essentially, you still need some kind of free fall to have the wave function expand.
Yeah, in our numbers, then we need sort of seconds to get the big superposition. And then if that's a drop, then that's many meters, but
And that's where the 2 seconds come.
where the what?
That's where the 2 second comes from.
Yeah, 2 seconds to sort of build up that superposition distance.
Okay, there's no other questions. Maybe we can thank Gavin again.